Today we're going to talk about an extremely important use of the definite integral, and that is to compute average values. Now, to get at average values, I want to consider how we compute average values for functions that are defined on a discrete domain. For example, suppose I measure 8 different people and their running times. Or maybe the 40-yard dash. And we're going to make this a little unrealistic, but if I take person number 1, 2, 3, 4, 5, 6, 7, and 8, and then I measure their times, and they come out to 10 seconds, 9 seconds, 10 seconds, 11 seconds, 12 seconds, 11, 12, and 9 again. And I ask you, what is the average time then you would represent that average time as 10 plus 9 plus 10 plus 11 plus 12 plus 11 plus 12 plus 9, and all of that divided by how much? Now, and we will call that the average time, just like that. If I were to represent that average time in a more compact notation, it would be this. It would be the sum of all of the times from I equals 1 to 8, not to infinity. And then it's divided by the number of things that I have. In fact, if you'll let me generalize a little bit, if I have n items, it's the sum from I equals 1 to n of ti, and all of that divided by n. Okay? Yes? The same, right? And here in this problem is yeah, Jason, they are the same meaning, and you can see that because if I let I equal 1, 2, 3, 4, 5, 6, 7, 8, then I am adding up each of the time values and then dividing them by the total number. So this is something you guys have been doing. When did you guys learn how to average? What grade? Second grade, sure. Second grade, third grade, fourth grade, something like that. You guys learned how to do it really, yeah, you've been doing it a long time. Now if I ask you this question. F of x equals x squared. What is the average value of f on the interval 0 to 3? Huh. That's interesting. The question kind of makes sense because my graph is going to go from 0 to 0 all the way up to 3, 9, right? And so the average value is in some sense the middle height, which looks like it's going to be somewhere around 4 or 5. I'm not so foolish as to think that it's going to be just 4.5, right? But the problem that I have is that if I try to use this approach right here, how many different function values do I have on the interval 0 to 3? I have an infinite number of function values. So I cannot accomplish averaging by directly adding up 1 to infinity and dividing by infinity. What does that even mean, right? But I can use a limit. So what I'm going to do is I'm going to take the interval from 0 to 3, and I'm going to partition that interval into some subintervals. It might make sense to partition them into subintervals of equal width. So let me try that a little better so they can be equally spaced. And for each subinterval, what I can now do is to sample my function by choosing one x value in that subinterval and finding the corresponding y value like that. And now the average value is approximately equal to the sum from I equals 1 to n of the value of my function at my choice, and all of that is divided by n. See, I'm doing here exactly what I did up here, but I am not able to capture every single point. I can only capture the samples. But now, if I let n go to infinity, then I really am capturing all of those samples, and I get a true average value. And this represents, as long as, now here's the key, as long as what I am doing is choosing one sample out of each subinterval, so that the widths of my subintervals is going to be 0. If I don't choose one x value out of each subinterval, then I will be over-counting some of the subintervals. Like it will be cheating to partition like this and then choose all of my x values out of all subintervals. I would get too high of an average. That would be biasing my result. Yes. The key is that CI has to belong to subinterval number I. I can't choose all of my C's out of the last subinterval and get a valid result. I have to choose one from each one. Yeah. But now I'm going to do something remarkable that's going to tie this to the definite integral. Because if you take a look at this n right here, this n I can rewrite as times 1 over n. And now I'm going to take that 1 over n and I'm going to think about what is that 1 over n. Well, when I did the equal space partition, what I did was to use a delta x that was equal to b minus a over n, right? And if I divide both sides by b minus a, then I find out that 1 over n is the same as delta x over b minus a. So that I can replace the 1 over n here with the 1 over n right there, and rewrite my sum, my average value sum, as the limit from I equals 1 to n. The limit as n goes to infinity of the sum from I equals 1 to n of f of ci times b minus a over n. Nope. Delta x over b minus a. There we go. That's the right substitution. Everybody with me? And now, something really nice is going to happen. Because I look at what I've got, and what I've got looks a whole lot like the limit of a Riemann sum, the limit of an area sum. But it's divided by b minus a. And the b minus a is constant. So I can factor out the 1 over b minus a and take the limit as n goes to infinity of the sum from I equals 1 to n of f of ci times delta x. And this is exactly the limit of a Riemann sum, which is a definite integral. This is exactly the same as 1 over b minus a times the integral from a to b of f of x dx. And that is our average value. Now this is a fascinating computation right here, and I want to explore it a little bit more. What does it mean geometrically? Remember that our definite integral means two things at once. It is the limit of the Riemann sum, it is also net signed area. So how do I interpret this in terms of net signed area? If I go back to my f of x that I had there, from 0 to 3, f of x equals x squared, then the integral from 0 to 3 of x squared dx represents the net signed area right here. And what I did was to take this whole area right here and to divide it by the width, 3 minus 0. And when I divide area by width, what I get is height, average height. Just as if I had taken a rectangle whose height is f average and computed its area right here. So geometrically, what we're doing when we find an average value is we're taking the total net signed area and we're dividing it by width to get an average height. And that corresponds nicely to taking the total sum of your items and dividing them by the number of items present. Well, how would we actually compute this? Well, we need some way to compute this integral. And we have a calculator that can do it for us. So let's go ahead and do that at this time. If I let y equal x squared, and I now integrate from 0 to 3, calculate it, get a value of 9. When you compute those average values, don't forget that your calculator is only giving you the area. It's not giving you the average value. Sometimes students will get so happy that they found the integral in the calculator, they tell me that the average value is 9. I know already that that's not possible because the maximum value up here happens to be 9. There's no way that my average value could be the max, right? So don't forget that you're computing the area on the calculator and then divide that by the width to get the average height, which is 3. Students are sometimes puzzled when they see that the average height is 3 because they see that the minimum height is 0 and the maximum height is 9, and so they reason incorrectly that the average height should be halfway between the min and the max. It should be 4.5, and it's not. Why not? The reason that it's not is that my function spends a whole lot more of its x values below 4.5 right here. It should be the case that when I find the average height, that the area that this rectangle includes that is not part of the curve should be equal to the area that the rectangle misses that is part of the curve. These two areas should cancel each other out. Does that make sense? Okay. Let's take a couple of minutes to practice computing average values in a variety of circumstances. And then I want to give you the idea of a couple of properties of the average value. Let's consider two different problems. First one is just going to be a straightforward computation. Find the average value if f is equal to e to the negative x squared on the interval 0 to 2. So first is our setup or representation. And we're going to represent that as total area divided by width, just like so. And then the second thing is the evaluation process. Of course, 1/2 is 1/2, but now we're ready for an integral. So we let y1 equal the desired function, like so. And we integrate from 0 to 2. And it thinks, gives us a value, 0.8821. And that gives us then 441 is the average value. Questions? I saw you guys were all computing along. Did you all get the same thing? Good?
Yeah, just do like calculate work out.
Oh, yeah, so one of the things you gotta be careful about, for some reason, the subtraction sign and the negative sign are different things. And so when you hit the go-to and it put that cursor right on the minus sign, that's why. And you should be good now. Uh-huh, you're welcome. I have no idea why TI decided to do that, but a little unfortunate. Okay, let's consider a second problem that would help us make a distinction here. Velocity of an object is given by v of t is equal to, oh, I don't know. On 0 to 7. And now I'm going to ask two different questions that are going to get at the heart of two different things that we have had that have both been called averages. First question. What is the average velocity on 0 to 7? And the second question, what is the average acceleration on 0 to 7? What is the average velocity, and what is the average acceleration? And the reason that I wanted to do these two questions is that they both have the word average in them, but one is asking about an average value, and one is asking about an average rate of change. And these two are not the same thing at all. The average value, and I know that this is an average value because it is asking me to find the average of the thing that is given. The average value is exactly what we've been talking about. To find the average value, we add up all of the values from 0 to 7 and divide by the total width. Let's go ahead and do that. Take a moment to use your calculators to find the average value. Actually, let me make sure my window size is good. Yeah, my window size was going to be a problem. See how my window size only goes up to 4? If I try to integrate from 0 to 7, it was going to fuss at me. Okay, let's get that integral going. 0 to 7. Think shade 11.1144. Is that what you got?
It's 16.1.
Oh yeah, you're right. You completely read that wrong. Notice that it is entirely possible to read your calculator wrong. So when I'm working on a test, very often I will double check and make sure that I have done that correctly. And here's a bonus. When you actually calculate the integral, it stores that value in the answer. So if I want to divide that by 7, then I can simply take my answer right here and divide it by 7. And that gives me the average value, 2.3021. But honestly, the safest way to do it would be to put a box around the answer right here. Okay? So that's the average value, and it's very straightforward. But this is, in part B, an average rate of change question, which we did all the way back when we did mean value theorem. Remember that? Average rate of change equals instantaneous rate of change at least one point if the function is well behaved. So, how do we distinguish these? First of all, how did I know this was an average rate of change? Because the acceleration is the rate of change of the velocity. So this literally is an average rate of change question. How do I compute that? I would compute that as a change in velocity over a change in time, or velocity at 7 minus velocity at 0 over 7 minus 0. And the velocity at 7 is pretty clearly 3, and at 0 is root 2. And all of that over 7, whatever number that may be. Here's the difference in terms of picture. My velocity function looks like this. This is v of t. And what the average height is doing is finding the middle height right here, which is 2.3021. There comes my average velocity. What the average acceleration is doing is finding the slope of the line connecting these 2 points. Right there. So they're asking completely different quantities here. Average height versus average slope. Here's a cool thing. We've got a minute, so I'll mention it. It looks like I ought to be able to compute the average acceleration as the average value of the acceleration. Shouldn't that make a whole lot of sense? It should make a whole lot of sense. I can, because when I add up the acceleration, what I get is the velocity. Which is exactly the computation of the But this requires me to jump ahead a little bit to a fundamental theorem to get there. So just don't worry about this right now. Think about this for this week and kind of chew on that for a little bit. The main thing to be learned here is how to pick out average values versus average rates of change. And the answer is that you pay attention to the wording in comparison to what you are given. Here I was given a velocity, and so the average velocity is an average value. Here I was given a velocity, the average acceleration is therefore literally the average rate of change, which is a slope. Yes, sir. If they give you position and you had to find average acceleration, it's kind of a weird question. That question probably would not be posed, and the reason it would not be posed is that, I mean, you could answer it And the best answer would be to use a derivative to find the velocity and then find the average slope of that. But it's an awkward, odd kind of question to ask.
You can also just do the, could you do the derivative velocity with the acceleration, just do the.
And do the average value of that, yeah. Yeah. And you
Same,
can,
right?
it's the same, that's right. It'd be the same as finding the slope of the velocity. Okay. The last thing that I want to do is to familiarize you with two properties, interrelated properties of average values. And the first one is the boundary property. And that is this. It's sort of obvious, but I'll just say it. The average value of a function must be trapped between that function's absolute minimum value and that function's maximum value. In other words, you take a look at this function right here. Its minimum value is all the way over here at A, and the maximum value occurs at B. Flush. And what this theorem states is that the average value, which looks like it's a little bit below, there we go, F average, has to be trapped in between the max and the min. Now, the reason for it is really simple. We all agree that by definition, here's our proof. By definition, f of x is trapped between its max and its min. That's what it means to be max and min. And if I now integrate this over a to b, actually if I just take the average value right here, then I have to preserve the inequality for the simple reason, remember that we had the domination property of our integral that said if f is bigger than g, then the integral of f is bigger than the integral of g, etc. But these two integrals right here are really easy. The integral of f min is the integral of a constant function, so that its value is exactly what you think it is. The average value of f min is f min. And likewise, the average value of f max is f max, which means that my average value is trapped between those two. So this is not surprising to us. We know this intuitively when we go averaging stuff, right? If you ask me, what's the average height of a person in this school? You're not going to pick 3 foot 8 inches. Because you figure that at worst there's like one little tiny 6th grader that's 3 foot 8 inches. And probably everybody in this school is 5 foot taller or higher, right? So the average height's got to be 5 foot something. And also, you're not going to pick 8 feet, because you know that the tallest possible person in the school that you can think of is going to be like 6'5", maybe, right? So the average has to be somewhere in between. Well, that's the spirit of this theorem. The average has to be somewhere in between. The second one is more profound. Does a function ever hit its average value? Can we be guaranteed that a function hits its average value? If it's continuous. Very good. That's exactly right. That's the condition that we need. So this is called the average value theorem. And it goes like so. If f of x is continuous, there is a C in A to B such that f of C equals the average value. And the picture practically proves the whole thing. I'll write the picture. I'll do the picture first, and then we'll. Let me make my function kind of funky. So let's pick a function that looks like this. And somewhere in here, since f is continuous on a closed bounded interval, f has to take on its max. That's the extreme value theorem. And somewhere in here, f has to take on its min, also the extreme value theorem. Which means that somewhere in between here, on this interval, f has to take on every value between the max and the min. And guess what? We already showed that the average value is between the max and the min. And so because the average value is between the max and the min, there has to be, we draw it probably about right here. There has to be at least one value of C, and that value is right here, where the average value hits the curve, just like that. Are there other values? Yeah, there are a couple other values over here. That's okay. But there has to be at least one. So let's take what we just said here and write it in math. Since f is continuous on A to B, there is, now I need to label this guy. Let's call that one x1. And let's call that guy x2. There is an x1 such that f of x1 equals f min. There is an x2 such that f of x2 equals f max. And that's by the extreme value theorem. And then, because f is continuous, but now it's continuous, it only needs to be continuous on x1 to x2, there is a C in x1 to x2 such that f of C is equal to f average, because f average is between f min and fx max. But what is f average? It is 1 over b minus a times the integral from a to b of f of x dx. And that's it. So tonight, what you're going to be doing is to be computing average values, and then tomorrow we'll extend this idea to area.